Good morning, everybody. We will be continuing our discussion on functions. We will clarify on a few things that we had briefly mentioned towards the end of the class, and then we will dive into trigonometry. For the first time in any of these classes, I don't think I have done trigonometry over the last year or so in these classes. Probably done it in some courses here and there. For some of you, those who are already proficient in trigonometry, I uh, request you to be a little patient in the first few minutes because they might be basic. And for those of you who feel I'm going fast, you can interrupt me anytime and ask me questions, and I'll be more than happy to reply. Okay, so we were studying about one-to-one functions and onto functions. And I finished off the class by telling you that the reason why we define all these functions like this is because we want to compare two sets, right? We have two sets and we want to compare their cardinalities, which is their size. We want to see how many elements there are, and we see if we can form a bijective function from one set to the other. And if that is so, then it means that both of them have the equal number of elements. If we cannot form a bijective function between the two sets, then it implies that one of those sets has more elements than the other, right? Uh, we proved last class that the number of even numbers is the same as the total number of numbers. We proved that the number of negative even numbers is the same as the total number of numbers. We can even prove that the number of prime numbers is the same as the number of composite numbers. And we had a lengthy discussion about the number of real numbers. Are they more than the natural numbers? And we said that the number of real numbers is more than the number of natural numbers. That's called an uncountable infinity. If you guys recollect, last year, actually, around this time, February of 2020, we had discussed something called the Hilbert's hotel paradox. And in that question, we were talking about having this infinite hotel, which has infinite rooms, and infinite guests show up. How do you place them in the rooms? Every single number which can be placed into the hotel is a countable infinity. Yes, Vansh remembers. Vansh, do you wish to tell us what you remember in a couple of sentences? If there is something that you recollect from that discussion, if you could share.
So there is basically a hotel, and it has an infinite number of rooms. And first, like a guest show up, and he says that first of all, then all rooms are occupied. Then a guest shows up and asks the managers, "I want to have some rooms." Now the managers ask him that how many people how many people do you want to book room? So he replies that I want for infinite people. Now our task is how to fit all these infinite people in that.
Okay.
So
Yeah. You wanted to say something else?
I wanted to tell that how do we do that?
Okay, no, don't reveal that. So that's okay. Thank you so much, Vansh. That's exactly what it was. This is an infinite hotel. It has infinite rooms, which are already full. We have almost every room has people there, and now we have new people coming in, and we have to fit them in the hotel. So I will not talk about this again, but I wanted to talk about this to tell you that we were discussing infinities over there as well. And what we were doing is forming a bijection between natural numbers and prime numbers, or natural numbers and rational numbers, or whatever that is. So you can look up more about the hotel paradox to see how different kinds of infinities can be fitted into this hotel. And that will be used to show that the number of primes is the same as the number of composites and all of those things. Also, so in terms of primes, what you could do is you can, so let's say we have infinite buses that come to the hotel, okay? And let us say that each bus has one prime number and each person is a prime number. So basically we want to put them in some room. So what we could do is we could send people to 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So there are infinite powers of 2. You can do the same for 3 to the power 1, 3 to the power 2, 3 to the power 3. There are infinite powers of 3, and none of them will match with any power of 2. So there's no clash. You can do the same for powers of 5. You can do the same for powers of 7 or any of those. So basically you can fit all natural numbers in just powers of one particular prime number. So you can send 3 to 2 to the power 3. You can send 10 to 2 to the power 10, and so on. So you can do that, and that way you can form a bijection between the powers of 2 and the entire natural number set. Or you can do it between the powers of 3 and the entire natural number set. So that's the kind of thing we can do to show that different infinities have the same quantity. Okay. So the study of calculus, which is probably the bedrock of all mathematics, almost every topic you learn in high school or college beyond 12th grade is built upon calculus. Real analysis, number theory, algebra, all of these things you require to you should understand what is calculus. And one of the fundamental tools towards understanding calculus is to study angles and to study trigonometry and the angles of shapes and the ratios of angles and curves of graphs and all of that. There's a raging debate in the mathematical community, and has been for a very long time now, as to whether calculus should be taught before trigonometry. And as I mentioned last time, I had the good fortune of studying both of them at the same time in the first ever Raising a Mathematician training program way back in 2014, I think. Mandar sir was teaching a little bit of calculus, and somebody else was, I think Hariharan sir was teaching a little bit of trigonometry. So both of them kind of were taught to me at the same time. And I never really was able to understand the point of trigonometry, and it was very difficult for me to keep track of all the names. Because as most of you might already be knowing, there are 5 or 6 different angles, and you always get confused as to what is what and what is the point of the whole thing. The first thing I wish to tell you is trigonometry is not just the study of triangles, although most of you might have seen trigonometry in a context where you have some sort of a right angle triangle, and you see the different angles and all of that. Because in ancient India, trigonometry was studied via a unit circle. The concept of trigonometry, you can kind of do it in any shape that you want, but it's always nice to do it from the point of view of a triangle, because there's a right angle, and most of those things kind of make intuitive sense. Okay, so before we even talk about complicated words like sine and cot and all of those things, I have a very simple question for all of you. If I have 3 objects, okay, let's forget about the triangle. Let's say I have 3 objects, and I have 2 chairs. So I have one chair here, and I have another chair over here. I have 3 objects. Let's say I have a book, a pen, and a phone. Each chair can hold only one object. My question to you is, in how many different ways can you put those 3 different objects on these 2 chairs? As an example, one way to do it is to put the pen on the yellow chair and to put the book on the blue chair. So in that sense, how many different ways are there in which we can arrange these 3 objects on these 2 chairs? If you get the answer, you can type it. Yeah, so I want the actual number. What is the number of different ways that you could put those 3 objects on these 2 chairs? Say one of them is pen and book. That's just one way to do it. Does order matter? That's a very good question. I'm glad you asked it. And yes, it does matter. So having a pen on the yellow chair and a book, actually let me write it with a different ink. We don't want to cause confusion. So having a pen here and a book here is not the same as having a book over here and a pen over here. So those are 2 different things. So order actually matters. How many possible ways? Okay, I'm getting a few answers, but I'm waiting for, let's say, 2 or 3 more answers, and then I can. Okay, so one says 12. Interesting. Shreyan says 6. Okay. There's a very simple way to do this without even listing all the different things. You can just think of it in a simple sense. How many different objects can you place on this one? How many different objects can you place on the first chair? 3, right? The 3 of them that you can place. We don't really care what you place first, what you place second. There are 3 different objects that can be placed on the first chair. How many different objects can be placed on the second chair? 3? No, because one of those objects has already been placed on the first chair. Remember, we don't have infinite pens and infinite books with us. We only have one pen, one book, and one phone. So if you can keep 3 objects on the first chair, you can basically keep only 2 objects on the second chair because you've already used up one slot. We don't know which object you placed on the first chair, but whatever it is, you've already used one object for the chair 1. So there are 2 different objects that you can place here. So the number of ways you can do it is 6. It's like saying if you have 3 shirts and 2 pants, how many different outfits can you wear? It's 6. Okay, so let's actually now list the different ways to do it. So one was phone and pen, one was phone and book, one was pen and book, one was pen and phone, and the other was book and pen and book and phone. Right, these are the 6 different ways we can do it. Do you agree with me, or did I leave out anything, or is there something that I've written twice? The order matters. So book and pen is not the same as pen and book. Those are 2 different chairs. Okay, agreed. Good. So now we will change our domain. Rather than saying I have 3 objects and 2 chairs, I will look at this shape which has 3 sides. Let's call it A, B, and C. Okay, 3 sides for this triangle. I want to pick 2 of them and I want to write them over here. I have 2 boxes, so in the top box I'll write one side, and in the bottom box I'll write one side. How many different ways can I do this? It's the same problem. We just changed the chairs to look like boxes, and we changed our objects to look like sides of a triangle. So the answer is still 6, because I can put 3 different sides on the top box. I can put 2 different on the bottom box. So I could, for example, I could do A over here, C over here. That's one way to do it. I could do A at the top, B at the bottom. Then I could do B at the top, C at the bottom, B at the top, A at the bottom, C at the top, A at the bottom, C at the top, and B at the bottom. So there's 6 ways to do it. Okay, so you all agree with this? We have not even changed anything to do with our logic. Instead of using pen, book, and phone, we just use A, B, and C, which are the 3 sides of the triangle, and we place them in that box. Why we place them in that box, we'll understand in a little bit of time, but we want to place them in that box. Okay. Now here comes the problem. Suppose somebody gave you the set of all these 6 different things, right? What you place at the top, what you place at the bottom. So one was AC, one was AB, one was BC, one was BA, one was CA, and the other was CB, right? Somebody does this and gives it to you. These are the 6 different ways you can arrange them. Now, you being the smart mathematician, asks that person, okay, I understand this. It makes sense. We have 6 different possible ways of arranging them, but which exactly is this A side, and which exactly is this B side, and which is this C side? Which sides are there? Because somebody might draw a triangle like this, somebody else might draw it like this. If you want to access one particular combination, how do you decide which one you choose? You don't know which side was B. We don't know how the original person drew this diagram. Let's say somebody in India draws this triangle and sends these combinations to somebody in America. How does that person know which sides of the triangle they were? Because A, B, and C seems very random. I could even name them P, Q, and R. So do you mean to say that just because I change some alphabets, all my combinations will change? Wherever I had A, C, A, B, and whatever, I now have P, Q, and PR, and all of that? We shouldn't allow such a system, right? That doesn't seem like a very reliable way of doing things. I have to come up with something more elegant. Okay, so I have this triangle. It's a right angle triangle, by the way. Is there a way by which I can define those sides somehow such that there is no ambiguity as to which side is what? Does anybody have any suggestion? If I name it A, B, and C, we are stuck because we don't know which side is A, we don't know which side is B. You cannot even tell, no, A is the side which is standing upright, B is the side which is falling down. What if somebody just looks at the triangle reverse? They don't know which is A, which is B. Any suggestions, guys, how to name the sides such that we exactly know which side we are talking about? Yes, it's
We
Manu.
can name them with respect to an angle. We can
Manu,
name them
I
with
think there's
respect to an angle.
I think there's some problem with your audio. Somebody else wants to say something. I think it is M Renganayaki, is it? Do you want to say something? Do you wish to share? No? Okay. Okay, so I was not able to quite catch on to what Manu said, but I did hear one word in his answer which is
So
very
this is
significant. Yes, Manu?
we can do it in respect to an angle.
Very good, very good. That's perfectly right. So for all of us who couldn't hear everything that he said, there's only one word which he said which matters a lot, and that is the word angle. Thank you, Manu. That's a very good answer. Rather than naming these sides A, B, and C, let us name them with respect to an angle. We don't want to name it with a right angle. That's boring. We already know the right angle. Let's look at this angle over here. There's an angle over here. Okay. Easy to understand. There's only 3 angles. We can pick that angle there. And we can now decide to name those sides based on that angle. That way they will stay the same. If somebody knows which angle we're talking about, they will automatically know all the 3 sides that we're talking about. So how can we name them with regard to the angle? One thing we could do to make things very simple is we can name the longest side as hypotenuse, because all of us know that the longest side in a right angle triangle is the hypotenuse, and there's only one possible side which can be the longest, because all of us know that the other 2 sides are shorter than the hypotenuse. This hypotenuse over here, this guy, he is the longest among the 3 sides, and you cannot draw a right angle triangle where something else is longer than the hypotenuse. It's literally not possible. So if we start off our adventure by naming this guy hypotenuse, we're not worried about what we are gotten rid of one side. The other 2 sides which we have to name, how can we name them based on that angle? Okay, so I see that one side, this side over here, is located far away from my angle, right? It's not even touching the angle, it's on the complete opposite side, whereas this side over here is located quite close to my angle. So I will name this guy close, and I'll name this guy far. We can name them anything. Let me actually use the same color for the far, so that we know what we're talking about. This wasn't exactly the same color, but you guys know what I'm talking. So we have 3 sides now. One is the hypotenuse. Everybody knows which is the hypotenuse. It doesn't matter how you draw the triangle. Doesn't matter whether you draw it on Mars or on Pluto or in India or in Nepal or America. It's the same thing. Hypotenuse is the longest side. We know which is the far side. The far side is the one that is opposite to the angle. There's only one side in the triangle which is opposite to the angle. That's that one. And we know which is the close side. It is the one that is right next to the angle. Absolutely no ambiguity. And we are talking about an angle which is not the right angle. I'm waiting for somebody to make an objection with this theory. This is like a small
Sir, but we can have an angle between far and hypotenuse of same kind, right?
Very valid point. Who told us that that angle is the one that we have to refer? Because if I don't know what angle I'm talking about, if this is the angle, the hypotenuse remains the same. That's still the longest side. He doesn't change. But the far and close will not remain the same. The close will now become the far because it is far away from that angle. And this pink far will become close to that particular angle, which I drew at the top. So they will change based on the angle. So in this whole mission of ours, we need to specify which angle we're talking about. And we will get to that in a minute. But as of now, let's imagine that that's easy to do. Let's specify that this is the angle we're talking about. We automatically know which are the 3 sides. Okay. Now that we have this whole toolbox set up, we have an angle, we have 3 sides. Let's go back to the thing that we did at the beginning of the class, where we want to arrange these 3 sides in place them on 2 boxes, and we can do it in 6 different ways. By the way, I mean, I don't know about you guys, but I'm not very comfortable about using this far and close because it doesn't feel technical enough. It feels more English than mathematics. The words that mathematicians actually use for these sides are opposite and adjacent. The close side is called adjacent. I'm sure most of you know the meaning of the word adjacent, right? He is sitting adjacent to me. Or if you say her house is adjacent to my house, it means that the house is right next to your house. Adjacent is right next. So it's the same meaning, but it's a lot more classical, right? Adjacent. It looks so much more mathematical, right? This is a close side, this is a far side. I mean, you don't even know what's a close, right? Is it nearby close? Is it shutting down, shutting open, or that close, or we don't know. And this far is called opposite. Opposite is something which all of us know. It's this is the side which is located opposite to our angle. So far, so good. Are you guys happy with opposite, adjacent, and hypotenuse? Somebody saying, isn't perpendicular also used for opposite? That's a good point. Perpendicular is something that forms a right angle with a straight line. Totally valid. But we have two perpendiculars in this side. Even the yellow side is perpendicular, right, to the pink side. We don't know which side is perpendicular. Both of them are perpendicular to each other. So if we say the opposite is perpendicular, then it becomes a little, when you just revert the triangle and make it stand up like this, right? For example, if the same triangle, I draw it like this is my yellow side, this is my purple side, and this is my hypotenuse. This is the same triangle, I just made it stand up. Now this becomes your perpendicular. It becomes a little confusing, so we'll stick with opposite, adjacent, and hypotenuse. Now let us look at all our 6 possibilities. So okay, have some patience because this is extremely tedious. What are the 6 different things? One is opposite, hypotenuse. Now you'll see why trigonometry is so beautiful. You don't have to do this all the time. One is hypotenuse, opposite. I mean, I cannot actually write this. This is too much. I'll write it with short forms. I'll say O is opposite, H is adjacent, and what is that? O is opposite, A is adjacent, H is hypotenuse. So I have O and H, I have O and A, I have H and O, I have H and A, I have A and O, and I have A and H. So these are the 6 different ways in which we can group them together. The whole point of trigonometry is to study the ratio of these sides. So what is the meaning of ratio? You take one number and you divide it by another number, it gives you the ratio. So if I have 3 glasses of milk on this side and I have 4 glasses of milk on this side, what is the ratio? It is 3 by 4, right? 3 divided by 4. For example, in my university, let's say we have 20,000 boys and we have 25,000 girls in the university. Now you want to know the ratio. You do 20,000 divided by 25,000. That gives you the ratio of the boys to the girls. So the whole point of trigonometry is to study the ratios of these sides. So we'll basically put a divided by sign everywhere. Is that okay? Is that looking too complicated? We didn't change anything. We just found out how many different ratios exist. There are 6 different ratios. The one ratio is you take the opposite side and you divide it by the hypotenuse, or you could take the opposite side and divide it by the adjacent, and so on. Ratio always has 2 terms. That's why we did that box. That's exactly why I told you there is a box where there's one term at the top and one at the bottom. This is the reason. This is the chair. You can think of the one as the chair where the numerator sits, other as the chair where the denominator sits. Any questions at this point? We have almost defined a very important term in trigonometry, but before I go there, I just want to make sure there's no confusion about this. We just found those 6 ratios of those 3 sides, and we have listed all of them here. Everybody understood? Okay, good. Very nice. Now the last thing here, just to be very elegant, just to be very nice, who in their right mind would want to refer to every ratio in these long names? Like, I want to talk about one particular ratio, right? I'll say opposite divided by hypotenuse. I say adjacent divided by hypotenuse. It is so long. Imagine writing this every time, and let's say they don't allow you to write these short forms, and you cannot write O and A because again it can be confusing. You should actually write opposite over adjacent, because O might mean somebody drew a triangle with O, A, and H, and they might have just randomly named the sides, right? You might do this as O, this as H, and this as A. You're just naming them. It's a triangle. You're not saying H is hypotenuse or O is opposite. So it gets confusing. So the last thing we will do is we will give a name to each of these ratios, so that when we talk about these ratios, we can talk about them from their name. Now, if somebody wants to talk about me, they don't want to talk about the 10 trillion cells in my body which are combined together to form some 200 plus bones and some nerves, right? You just want to refer to me as Raghav with one simple name. We should give a small name to talk about something a lot more complex. So let's do it. So we have 6 ratios. Okay. Opposite over hypotenuse is called sine. Adjacent over hypotenuse is called cos. And opposite over adjacent is called tan. We'll just worry about these 3 now. There are 3 more, right? There were 6 ratios in total, but we will not talk about them now because they are just the inverse of all these 3 ratios. If you look at the things that I've written down and the things that I had left out, what are the things that I had left out? One was h over o. That's just the reverse of the first one. The other was h over a. That's just the reverse of the second one. And the third one was a over o, and that's the reverse of the third one. So we'll just talk about these 3. The other 3 are the inverses of these 3. Does that make sense? Is that are you guys comfortable with this arrangement, that we deal with these 3 because the other 3 are reverses of these? Good. So whenever we want to talk about this particular ratio, which is talking about opposite side divided by the hypotenuse, we call it sine. Adjacent side divided by hypotenuse, we call it cos. Opposite side divided by adjacent side, we call it tan. To be very honest with you guys, even this guy is not required. Can you tell me why this is not required? So I want to give you a small exercise. Look at sine, look at cos. Can you do something to those 2 ratios and arrive at tan? Can you add them both together and get tan, or multiply, or can you do something to those 2 ratios and just arrive at the third one? We have o divided by h, we have a divided by h. Now I want to get o divided by a. How can I get it? Is there a method that anybody would like to suggest? Assume we don't know what is tan, but we know what is o over h, which is sine. We also know what is a over h, which is cos. Using these 2, I want to arrive at o divided by a, which is this tan. O divided by a. Can you get o divided by a just using o divided by h and a divided by h? I'm getting some very nice answers. Good, good. I got 2 answers which I think are correct. I'll just wait for somebody else to give me another right answer. I at least need 3 answers to hope that most of you might have gotten it right. Good, very good. It is just this thing divided by this thing. Just think about it. What will happen if you divide that thing by that thing? Now we're talking about something a little complicated here. Let's erase this. Let's make it very clean. Let's write using white, plain white. So the first thing that we had was o over h, right? The second thing that we had was a over h. Now what I wish to do is divide the first one by the second one. So basically what I want to do is this. I'm dividing one division by another division. Right? I want to divide both of them. What will happen when I divide both of them? I have o divided by h. That guy looks like a man for some reason. The o divided by h, it looks like a boy. Anyway, so we have o divided by h divided by a divided by h. So these h's get cancelled, right? They're on either side of the fraction. We can just get rid of them. It's just o divided by a. For those of you who know division is the reciprocal of multiplication. So if you do o divided by h times h over a, the 2 h's get cancelled and you get o divided by a, which was the definition that we gave for the third ratio. We already had this ratio, we had this ratio. Using those 2, we can generate this one. So the first thing that we will learn for today is the first trigonometric identity is sine divided by cos is equal to tan. This is very, very, very important. Sine was O divided by H, cos was A divided by H, and tan is O divided by A. Opposite divided by hypotenuse, divided by adjacent divided by hypotenuse, gives us opposite over adjacent. Any questions at this point of time? Okay. Now let us see this in reality, how these guys actually look. Let me have this beautiful right angle triangle, and I'll put the sides which are my favorite: 3, 4, and 5. This is my favorite right angle triangle. I mean, 3 squared plus 4 squared is 5 squared. So this is a legal right angle triangle. It's not like I'm just putting some numbers randomly. This is a right angle triangle. Let us define this as our angle. First question I want to ask you guys is, can you tell me what is the measurement of the opposite side? What is the measurement of the adjacent side? And what is the measurement of the hypotenuse? You just type in the chat O equals something, A equals something, and H equals something. Can you type it in the chat for me? So type what is equal, what is H, good, what is A, and what is O. Very good, very good. Good. So far, all of you have gotten it right. Just wait for a couple more answers, and yeah, somebody wants to say something? Omkar, you have a question? No? Okay, I think you unmuted by mistake. Good. So O is equal to 3, A is equal to 4, and H is equal to 5. Is that right? Let's just write it here now. Let's write it using some other color. O equals 3, H equals 5, and A equals 4. Let's call this guy X, our favorite number X, favorite variable X. This is angle, it's some angle, we don't know what it is. Now, we will get back to the question that was asked by somebody when I defined this rule. Somebody said, how in the world do you know that that is the angle? What if it's the other angle here, right? Let's say there's another angle over there. Why? Well, this is right angle, but there are two different angles. We don't know what they are, but the ratios can change depending on which is the angle, right? Now, opposite is 3. If X is being used, but if we use Y, then opposite becomes 4 and adjacent becomes 3. Is that right? So we will now look at everything from the point of view of X. We'll not look at Y, we'll only look at X. So from the point of view of X, 3 is opposite, 4 is adjacent, and 5 is hypotenuse. What is the value of sine of X in this particular diagram? Sine is opposite divided by hypotenuse. That is the ratio which we use for sine. Can somebody tell me what is the value of sine X in this triangle? 3 over 5. Very good. Very good. Sine X equals 3 over 5. It's not 3 is to 5, it's 3 over 5. Yeah, it's a ratio, but we like to write it as a fraction. A slightly tricky question. Can somebody tell me what is sine of Y in the same shape? Good. Very good. Sine of Y is 4 over 5 because the opposite side then is the 4. If you look at, from Y's perspective, opposite is 4, adjacent is 3, and hypotenuse is 5. So the sine of Y will be 4 over 5, but the sine of X will be 3 over 5. Right? Now let's look at the other ratio, which was cos. Cos is adjacent over hypotenuse. So then the cos of X will be 4 over 5 because 4 is adjacent to X. But the cos of Y will be 3 over 5. You agree with me? Okay. Before we end today's session, there is one last fact that I want to give you, which is why this whole branch of trigonometry is so useful. Yeah, somebody asked, why do we need this fraction, right? That's exactly what I wish to share with you. This particular angle x, okay, we don't know what that angle is right now. But suppose we were to fix that angle. Let's say we wanted to make it some angle, right? Let's say we make it 50 degrees or we make it 30 degrees or whatever that is, right? The incredible thing is, no matter how big the triangle is, no matter who draws the triangle, no matter what color you use, that ratio of sine will remain the same, that ratio of cos will remain the same, and each of those 6 ratios will remain the same if you decide what your x should be. Now all of that ambiguity is gone, right? We don't care about which angle, we don't care about which side, we don't care about the ratio, nothing. If you tell me that angle x equals some degrees, let's say it is 30 degrees, I can tell you every single ratio because they are fixed for a given angle. It won't change no matter how big the triangle is. If my triangle is this big and if I have this angle as 30 degrees, or if my triangle is this big and if I have this angle as 30 degrees, the opposite divided by adjacent or the opposite divided by hypotenuse will remain the same. So as a side fact, sine of 30 degrees is 1 by 2. So if you draw a triangle, if you draw a right angle triangle and you pick any of those angles which are 30 degrees and you compare opposite divided by hypotenuse in that triangle that you drew, you will get 1 over 2. And this is my challenge to you. You can draw any triangle that you want, as big as you want, as small as you want, as long as one of those angles is 30 degrees and you look at the opposite of that angle and the hypotenuse of that angle, it will be 1 over 2. So it might be 10 divided by 20, or it might be 50 divided by 100. It might be trillion divided by 2 trillion, depends how big you draw it. It will be 1 over 2. Okay, so this is why trigonometry is important. It teaches us the ratios of right angle triangles. That's saying I will stop the recording and see you all next week.